Welcome to Sleep Scholars, a sanctuary where science and serenity meet to guide you toward deeper rest. Tonight, as with every night, we're grateful to share this journey with you. Before we begin, a heartfelt thank you to our brilliant team of writers, whose work transforms research into stories meant to calm, heal, and inspire. And now, I'm honored to hand you over to the soothing voice of James Parker, who'll gently lead you through the rest of this evening. If you'd like Sleep Scholars to be part of your nightly ritual, hit subscribe. We'll always be here when you need us. James, take it away.
Thank you, Michael. Friends, wherever you are, whatever weighs on you, let's begin. Ethical quandaries abound. Who is responsible if an AI makes a fatal error? Should autonomous robots have the right to alter their programming if they encounter unforeseen scenarios? And as machines grow more sophisticated, could they develop forms of consciousness, or at least a semblance of it? Philosophers and scientists debate these questions, but space offers a unique testing ground. The vacuum of space is unforgiving, and mistakes are lethal. Yet it is also a realm of infinite possibilities, where the rules can be rewritten. The rise of AI also redefines our search for extraterrestrial intelligence. If advanced civilizations exist, they may have long since merged with machines, their biological forms obsolete. SETI's traditional search for radio signals might be akin to scanning the jungle for smoke signals while missing the city's Wi-Fi. New initiatives, like the search for technosignatures, focus on signs of advanced technology, laser propulsion systems, Dyson swarms capturing starlight, or even the waste heat of megastructures. AI is crucial here, sifting through petabytes of data to find patterns invisible to humans. Closer to home, AI is reshaping our understanding of the cosmos itself. Projects like Google's DeepMind have developed algorithms that predict the structure of the universe with startling accuracy, simulating galaxy formation in microseconds, a task that would take supercomputers months. Other AIs analyze gravitational wave data from LIGO, identifying collisions of black holes and neutron stars buried in the noise. In a sense, these machines are becoming scientists in their own right, generating hypotheses, testing theories, and even discovering anomalies that challenge our models. But the universe guards its secrets jealously. Dark matter, dark energy, the nature of time, these mysteries persist, resisting even the most advanced algorithms. Perhaps AI will crack them, finding patterns in the chaos. Or perhaps these enigmas will humble our machines, revealing the limits of silicon and code. What lies ahead is a future where exploration is no longer constrained by human lifespans or biology. AI-driven probes could endure centuries-long journeys to the Oort cloud, surviving on nuclear batteries and self-repairing circuits. Swarms of nanobots, smaller than grains of sand, might explore the subsurface oceans of Europa, swimming through icy fissures and mapping alien ecosystems. And in the far future, von Neumann probes, self-replicating robots that mine asteroids to build copies of themselves, could spread across the galaxy, a wave of mechanical life expanding exponentially. Yet this future is not inevitable. It depends on choices we make today. Will we wield AI as a tool for collective uplift, or repeat the mistakes of the past, weaponizing and monopolizing it? The answer may determine whether we become a spacefaring civilization or remain forever tethered to Earth. For now, the partnership between human and machine grows ever deeper. Astronauts on the ISS converse with AI assistants that manage life support and experiment schedules. On Earth, engineers use virtual reality and AI simulations to train for Mars missions. And in labs worldwide, scientists are teaching robots to think like biologists, geologists, and physicists, preparing them to be our eyes and hands on worlds we cannot yet reach. The machines among us are more than tools. They are the inheritors of our curiosity, the vessels of our ambition. They will go where we cannot, survive what we cannot, and see what we cannot. And in their cold, precise way, they will carry the essence of humanity, the relentless drive to explore, into the cosmic dark. The next chapter in this saga will venture into the realm of the unimaginable, black hole laboratories, quantum sentience, and the paradoxes of time travel. It is a story of theories so radical they defy intuition, and technologies so advanced they border on magic. The universe, ever enigmatic, refuses to yield its truths easily. But with machines as our allies, we are closer than ever to piercing the veil. Black holes are the universe's most perfect paradoxes, objects so dense that light cannot escape them, yet paradoxically, they are also among the brightest phenomena in the cosmos when they feed. They are born from the deaths of massive stars, collapsing under their own gravity into singularities, points where the laws of physics as we know them cease to function. Around these singularities lies the event horizon, a boundary that marks the point of no return. To cross it is to be stretched and compressed by tidal forces, a process grimly nicknamed spaghettification, until every atom is torn apart. But black holes are more than cosmic shredders. They are engines of creation. When they consume matter, they spew jets of particles and radiation at nearly light speed, igniting star formation in distant galaxies and seeding the cosmos with heavy elements. In 2019, humanity glimpsed the shadow of a black hole for the first time. The Event Horizon Telescope, a global array of radio telescopes, captured the glow of superheated gas swirling around M87*, a supermassive black hole 55 million light-years away. The image, a fiery ring framing a dark void, confirmed Einstein's century-old predictions about spacetime's curvature. 2 years later, the same collaboration revealed the turbulent magnetic fields around Sagittarius A*, the Milky Way's own supermassive black hole. These observations are not just scientific triumphs, they are visceral reminders of how small we are in a universe where monsters lurk in the dark. But black holes are not eternal. In 1974, Stephen Hawking proposed that quantum effects near the event horizon cause black holes to emit radiation. Over incomprehensible timescales, they evaporate, their mass dissolving into a faint glow of particles. For stellar black holes, this process takes longer than the current age of the universe. For hypothetical primordial black holes, tiny ones forged in the Big Bang's chaos, evaporation might explain fleeting bursts of gamma rays observed in the sky. Hawking's theory bridged relativity and quantum mechanics, two pillars of physics that otherwise refuse to speak. Yet it also birthed a paradox. If a black hole evaporates, what happens to the information it swallowed? Quantum mechanics insists information cannot be destroyed, but black holes seem to erase it. The debate rages. Some argue the information is encoded in Hawking radiation, leaking out in scrambled form. Others propose it is stored on the event horizon, a holographic ledger of everything that fell in. This puzzle is part of a grander quest, the search for a theory of quantum gravity. Einstein's relativity describes spacetime as a smooth fabric bent by mass and energy. Quantum mechanics paints particles as probabilistic waves. Merging these frameworks would unravel the universe's deepest secrets, from the Big Bang's first moments to the singularity's heart. String theory, one candidate, posits that particles are vibrations of infinitesimal strings in 10-dimensional space. Black holes, in this view, are tangled knots of strings, their entropy tied to the number of vibrational configurations. Another approach, loop quantum gravity, quantizes spacetime itself into discrete atoms, preventing singularities by replacing them with Planck stars, dense remnants that bounce rather than collapse. Both theories remain unproven, but experiments inch closer. Gravitational wave detectors like LIGO and Virgo listen for subtle deviations and black hole mergers that might betray quantum gravity's fingerprints. Spacetime, as Einstein revealed, is not a static stage, but a dynamic actor. Massive objects warp it, and collisions send ripples, gravitational waves, racing across the cosmos. In 2015, LIGO detected waves from two merging black holes, a discovery that earned a Nobel Prize. These waves are not just cosmic messengers, they are echoes of spacetime's flexibility. Yet spacetime's true nature is stranger still. The universe is expanding, and not just expanding, accelerating. Dark energy, an unknown force permeating the vacuum of space, drives this acceleration. It constitutes 68% of the universe's energy, yet its identity remains a mystery. Is it Einstein's cosmological constant, an immutable energy woven into spacetime? Or a dynamic field that evolves over time? The answer shapes the universe's fate: endless expansion, a catastrophic big rip, or a cyclical rebirth. Dark matter, meanwhile, binds galaxies and clusters with its invisible grip. It outweighs ordinary matter 5-1, yet refuses to interact with light. Particle colliders, underground labs, and space telescopes hunt for clues. Is it a yet undetected particle? A cosmic relic from the Big Bang? Or a sign that gravity works differently on large scales? The answer eludes us, but its presence is undeniable. Without dark matter, galaxies would fly apart, their stars' orbital speeds defying Newtonian gravity. At the quantum scale, spacetime itself seethes with activity. Virtual particles, pairs of matter and antimatter, blink in and out of existence, borrowing energy from the vacuum. Near a black hole's event horizon, one particle may fall and while the other escapes, manifesting as Hawking radiation. This process suggests black holes are not truly black but emit a faint glow, their temperatures inversely tied to their mass. For a stellar black hole, this temperature is a billionth of a degree above absolute zero, undetectable in practice. For a microscopic black hole, it would be a fiery inferno. The holographic principle deepens the strangeness. It proposes that all information within a volume of space can be encoded on its boundary, like a 3D hologram projected from a 2D surface. Applied to black holes, this resolves the information paradox. Data swallowed by the singularity is preserved on the event horizon, escaping as Hawking radiation. The universe, in this view, is a hologram, its true nature written on a distant, invisible surface. Time, too, bends under extreme gravity. Near a black hole, clocks tick slower, a phenomenon verified by GPS satellites, which adjust for Earth's weaker time dilation. But can time travel backward? Wormholes, hypothetical shortcuts through spacetime, offer mathematical pathways to the past, but stabilizing them requires exotic matter with negative energy, a substance theorized in quantum fields but never observed. Even if possible, paradoxes loom. A traveler could return to kill their grandfather, erasing their own existence, a logical impossibility that suggests nature forbids such loops. Today's experiments probe these frontiers. The Large Hadron Collider smashes particles to recreate the Big Bang's fireball, seeking clues to dark matter or extra dimensions. Quantum computers simulate spacetime's fabric at the smallest scales, testing theories of quantum gravity. Telescopes like Euclid and the Nancy Grace Roman map dark energy's influence, while the IceCube Neutrino Observatory in Antarctica detects ghostly particles from black hole jets and supernovae. Yet for all our tools, the universe guards its secrets. 95% of it, dark matter and dark energy, remains unknown. The singularity's heart is veiled, and spacetime's quantum weave resists unraveling. But this ignorance is not failure, it is invitation. Every unanswered question is a door, every paradox a path. As we stand on the shoulders of giants, Einstein, Hawking, Penrose, we glimpse horizons once unimaginable. The journey is endless, the cosmos unyielding, but the human spirit, relentless and curious, presses onward. The universe, as we perceive it, is a vast and intricate tapestry of galaxies, stars, and planets, a single thread in a loom that may weave endlessly beyond the edges of our observation. But what if our universe is not alone? What if it is one of countless others, each with its own laws of physics, its own histories, its own versions of life and death? This is the realm of the multiverse, a concept that stretches the imagination to its limits, challenging our understanding of reality itself. The idea emerges not from science fiction, but from the cold equations of physics, where the mathematics of cosmic inflation, quantum mechanics, and string theory suggest that our universe might be a single bubble in an infinite froth of universes, each born from the same primordial chaos, but evolving into wildly different forms. Cosmic inflation, the rapid expansion of space in the universe's first moments, provides one pathway to the multiverse. According to inflationary theory, the vacuum of space is not truly empty but seething with energy. In the early universe, this energy drove exponential expansion, smoothing space-time and planting the seeds of galaxies. But inflation does not end everywhere at once. In some regions, it stops, creating a stable universe like ours. In others, it continues eternally, spawning new universes in a process called eternal inflation. Each of these bubble universes forms its own cosmos, with physical constants and dimensions that may differ from our own. Some might have stronger gravity, making stars burn brighter and die younger. Others might lack electromagnetism, rendering chemistry impossible. A rare few, by chance, could have the precise conditions for life. This cosmic Darwinism suggests that we inhabit a universe suited to us not by design but by statistical inevitability, a survivor in a sea of failed experiments. Quantum mechanics offers another route to the multiverse. The many-worlds interpretation posits that every quantum event splits reality into parallel branches. When an electron passes through a double slit, it doesn't choose a path, it takes both, spawning two worlds, one where it went left, another where it went right. Applied universally, this implies a near-infinite array of timelines diverging with every particle interaction. In one world, dinosaurs still roam Earth because the asteroid missed. In another, you never existed. While this interpretation remains controversial, it highlights the strangeness of quantum theory, where observation collapses probabilities into singular outcomes, or, in the many-worlds view, preserves all outcomes in separate realities. String theory, the ambitious framework seeking to unify all forces of nature, adds another layer. It suggests that our universe's three dimensions of space and one of time are not fundamental but arise from the vibrational states of tiny strings. These strings exist in a 10 or 11-dimensional bulk space, where each set of folded dimensions corresponds to a different universe with unique physics. In this brane multiverse, our universe might be a three-dimensional membrane, or brain, floating in a higher-dimensional void, occasionally colliding with others. Such collisions could trigger Big Bang-like events, resetting cosmic history. But how do we test these theories? Evidence for the multiverse is elusive, as by definition, other universes lie beyond our observational horizon. Yet subtle clues might linger. The cosmic microwave background, CMB, the afterglow of the Big Bang, could bear imprints of collisions with other bubbles in the inflationary froth, anomalous cold spots or swirling patterns in the ancient light. So far, searches have found nothing definitive, but the hunt continues. Meanwhile, particle accelerators like the Large Hadron Collider probe extra dimensions predicted by string theory, seeking particles that briefly disappear into higher dimensional space. The multiverse idea forces us to confront the anthropic principle, the observation that our universe's laws seem finely tuned for life. If only one universe exists, this tuning seems miraculous, a stroke of cosmic luck. But in a multiverse, it becomes statistical necessity. With infinite universes, every possible combination of physical constants exists somewhere. We find ourselves in a universe that permits our existence, while countless others, inhospitable to life, go unobserved. Critics argue this reasoning is circular, a retreat from deeper explanation. Advocates counter that it is no different from noting Earth's position in the solar system's habitable zone, a selection effect, not a design. Beyond the multiverse lies the question of time itself. Is it linear, an arrow flying from past to future, or an illusion woven from entropy and memory? The second law of thermodynamics dictates that entropy, a measure of disorder, increases over time, giving rise to the one-way flow we experience. But in a multiverse, where time might behave differently in each bubble, could some universes run backward, their inhabitants remembering the future? Quantum gravity theories suggest time may emerge from more fundamental, timeless processes, like a movie projected from static frames. The universe's ultimate fate hinges on dark energy. If it remains constant, the cosmos will expand forever, galaxies receding until their light fades from view. Stars will burn out, black holes evaporate, and space descend into a lifeless, frigid void, a heat death. If dark energy strengthens, it could tear apart galaxies, stars, and even atoms in a big rip. Alternatively, gravity might reverse the expansion, pulling everything back into a big crunch, a fiery rebirth that could spawn a new universe. Cyclic models propose endless oscillations between expansion and contraction, each cycle erasing the past and birthing anew. Humanity's quest to grasp these mysteries is both humbling and heroic. We send probes to the edges of the solar system, build telescopes that peer back to the dawn of time, and dream of equations that might unite quantum and cosmic scales. Yet the more we learn, the vaster the unknown becomes. The multiverse, quantum realms, and spacetime's enigmas are not just scientific problems, they are existential mirrors, reflecting our longing to understand our place in the infinite. As we gaze into the night sky, we are not just observers but participants in a story 13.8 billion years in the telling. Each discovery, from the Higgs boson to gravitational waves, adds a verse to this epic. And though the answers may lie beyond our reach, the act of seeking defines us. We are the universe made conscious, the cosmos contemplating itself, a flicker of awareness in the dark, reaching for light. Humanity's relationship with the cosmos has always been one of paradox, a species tethered to a single planet yet endlessly reaching beyond it. For millennia, we mapped constellations and tracked seasons, aligning our myths and harvests with the stars. Today, we stand on the precipice of a new era, where technology transforms us from passive observers to active participants in the cosmic drama. Satellites thread the skies, telescopes dissect ancient light, and rovers tread alien soils. But this is only the beginning. The next century may see humans become an interplanetary species, our ambitions stretching from Martian colonies to asteroid mines, our machines probing the icy moons of Jupiter and the winds of distant exoplanets. The International Space Station, ISS, a marvel of global cooperation, orbits Earth every 90 minutes, a symbol of what humanity can achieve when curiosity transcends borders. Astronauts aboard the ISS conduct experiments in microgravity, studying everything from protein crystallization to the effects of long-term spaceflight on the human body. These studies are not abstract curiosities, they are stepping stones to Mars and beyond. NASA's Artemis program aims to return humans to the moon by 2025, establishing a sustainable lunar base as a proving ground for deeper exploration. The moon's poles, shrouded in permanent shadow, harbor water ice, a resource that could be split into hydrogen and oxygen for fuel and life support. From there, Mars beckons. Elon Musk's SpaceX envisions a self-sustaining city on Mars within this century, a vision both audacious and fraught with peril. The challenges are legion: radiation exposure, toxic soil, and the psychological toll of isolation. Yet the dream persists, fueled by the knowledge that Earth, for all its beauty, is fragile. A single asteroid, supervolcano, or self-inflicted catastrophe could erase millennia of progress. Becoming multiplanetary, proponents argue, is not just exploration, it is insurance. But space is no longer the domain of governments alone. Private companies like Blue Origin, Rocket Lab, and Astra are democratizing access to orbit, slashing launch costs and enabling startups to deploy satellites for weather monitoring, internet access, and environmental tracking. CubeSats, no larger than a shoebox, now swarm in low Earth orbit, their cameras mapping deforestation, tracking wildfires, and monitoring coral reefs. This democratization carries risks. Space debris, a growing threat, could render key orbits unusable if left unchecked. Over 30,000 trackable objects, dead satellites, spent boosters, shrapnel from collisions, already litter the skies, a testament to humanity's carelessness. Solutions like robotic garbage collectors and biodegradable satellites are in development, but the problem underscores a broader truth: our ventures into space must balance ambition with stewardship. Beyond survival and profit lies a deeper motive: the search for meaning. Robotic missions to Europa and Enceladus aim to probe their subsurface oceans for life. The James Webb Space Telescope peers into the atmospheres of exoplanets, hunting for biosignatures like oxygen or methane. Breakthrough Listen scans the galaxy for technosignatures, radio signals, laser pulses, or other evidence of intelligence. These quests, however uncertain, address a primal question: are we alone? The answer, whether yes or no, will redefine our understanding of existence. Yet space is not a panacea. Earth's problems, climate change, inequality, war, cannot be escaped by fleeing to Mars. Critics argue that resources spent on space exploration would be better directed towards solving terrestrial crises. This dichotomy is false. The technologies born from space research, solar panels, water filtration systems, medical imaging, have already transformed life on Earth. Moreover, the cosmic perspective fosters unity. The overview effect, described by astronauts who've seen Earth from space, imparts a profound sense of interconnectedness, a realization that borders and conflicts are trivial against the backdrop of a fragile blue marble. The future of humanity in space hinges on choices made today. Will we weaponize orbit as nations test anti-satellite missiles and draft laws for lunar mining? Or will we forge treaties akin to the Antarctic Accords, preserving space as a commons for all? The Artemis Accords, signed by 30 nations, offer a framework for peaceful lunar exploration, but enforcement remains nebulous. The stakes are cosmic. The choices of this generation will echo for millennia. In 1990, as the Voyager 1 spacecraft sped toward the edge of the solar system, Carl Sagan requested it turn its camera homeward. The resulting image, the pale blue dot, shows Earth as a speck of light suspended in a sunbeam, a mote of dust adrift in the vastness. Sagan's reflection on the image endures as a manifesto of humility and wonder. Every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. This image encapsulates the human condition. We are finite beings in an infinite universe, endowed with the ability to question, create, and dream. From the first sparks of consciousness around a fire to the silent glow of computer screens on the ISS, our story is one of curiosity overcoming limitation. We have decoded the genomes of extinct species, reconstructed the lives of stars, and sent messages to the stars. Yet for all our achievements, we remain humbled by the cosmos' scale and mystery. The universe's 13.8 billion year saga, from singularity to quarks, stars to planets, microbes to minds, is a tale of transformation. Hydrogen, forged in the Big Bang, became the water in our cells. Carbon, born in stellar cores, became the backbone of DNA. Gold, cast out in neutron star collisions, became the symbol of our aspirations. We are stardust, yes, but stardust that writes sonnets, builds telescopes, and wonders why. Our quest is unending. New generations will probe black holes for quantum secrets, dive into Europa's oceans with autonomous drones, and decode signals from civilizations older than the sun. They will confront new paradoxes, new crises, and new wonders. Some may walk on Mars, their boots sinking into red dust, and gaze at Earth as a faint star in their twilight sky. Others may launch probes to Alpha Centauri, carrying humanity's greetings to whoever or whatever awaits. But the essence of exploration is not conquest or escape. It is the act of reaching, of pushing against the boundaries of the known. It is the child pointing to the night sky, asking, "What's out there?" It is the scientist laboring over equations by lamplight, the engineer refining a rocket's curve, the poet finding metaphors in the Milky Way. The cosmos does not care if we succeed or fail. It does not judge our wars, our art, or our love. Yet in our insignificance lies our freedom. We are not the universe's purpose, but we are its storytellers. With each discovery, we reweave the narrative of existence, adding our chapter to a saga that began with light-piercing darkness. As the stars burn on and galaxies spin into the void, humanity's legacy will not be measured in light years or megatons, but in the questions we dared to ask and the courage to live without answers. The universe is not a puzzle to be solved, but a mystery to be cherished, an endless horizon inviting us to wander, wonder, and belong. We are stardust that learn to wonder, atoms forged in dying stars, woven into beings who gaze at the night sky and dare to ask, why? Our journey, from the first sparks of fire to the silent glow of satellites, is a testament to curiosity's power to transcend the limits of flesh and time. We have mapped the cosmic web, heard black holes collide, and touched the soil of other worlds. Yet the universe remains vast, its secrets veiled, its horizons endless. The true legacy of our exploration lies not in the answers we've found, but in the questions we've awakened. Every mystery unraveled births 10 more, each a thread in the infinite tapestry of existence. We are fleeting, yes, a flicker of light in the cosmic dark, but we are also luminous. In our art, our science, and our stubborn hope, we turn the void into a mirror, reflecting back the beauty and terror of being alive. As the stars will onward, let us go gently into that expanse. Let us carry the fire lit by ancestors who painted constellations on cave walls and named gods in the world of galaxies. Let us build not just for ourselves, but for the generations who will sail solar winds and dream of shores beyond our sight. The cosmos does not belong to us, but we belong to it, a small, brave chorus in the grand, silent song of existence. And so the story continues. Not with an ending, but with an ellipsis. Yet the first stars did more than create elements. Their light ended the universe's dark ages, and their explosions triggered waves of star formation that rippled through galaxies. They also left behind another puzzle, dark matter. Though invisible, dark matter's gravitational pull shaped the distribution of galaxies. It clumped into vast halos, creating a cosmic web of filaments and voids. Ordinary matter, the stuff of stars and planets, flowed along these invisible rivers, pooling at the intersections. The largest structures in the universe, galaxy clusters, formed at these nodes, bound together by dark matter's embrace. The cosmic web is not static. It evolves, driven by dark energy, a mysterious force causing the universe's expansion to accelerate. In the early universe, gravity dominated, pulling matter into dense structures. But as dark energy's influence grew, it began to counteract gravity's pull, stretching space itself. Galaxies not bound by gravity's grip began to drift apart, their light stretched into longer wavelengths, a phenomenon we observe as redshift. The legacy of the first stars is written in the sky. Modern telescopes, like the James Webb Space Telescope, peer back in time to glimpse their faint light. These observations reveal galaxies in the early universe, small and chaotic, ablaze with star formation. Their spectra bear the fingerprints of heavy elements, evidence of earlier stellar generations. Yet the first stars themselves remain elusive, their light too dim and redshifted to detect directly. To study them, astronomers rely on simulations and indirect clues, the chemical composition of ancient stars, the structure of the cosmic web, and the shadows they cast on the CMB. The story of the first stars is also a story of extremes. They existed in a universe far hotter, denser, and more chaotic than our own. Their formation required pristine gas, unsullied by the debris of earlier stars. As the universe aged, such gas became rare. Today, star formation occurs in environments rich in metals, producing smaller, longer-lived stars. The era of the first stars was a fleeting chapter, a violent prelude to the more orderly cosmos we inhabit. But their influence endures. The elements they created enabled the chemistry of life. The black holes they seeded grew into giants, shaping galaxies. Their light ended the darkness, illuminating the universe for the first time. And their deaths set in motion the processes that would lead, billions of years later, to planets, oceans, and beings capable of contemplating their origins. As we study the first stars, we confront fundamental questions. What triggered the collapse of the first gas clouds? How did dark matter guide their formation? What role did magnetic fields play? Each answer peels back a layer of mystery, revealing deeper questions. The universe, it seems, is a puzzle with infinite pieces. The next chapter in this cosmic saga is the rise of galaxies. From the ashes of the first stars, galaxies began to assemble, spirals, ellipticals, irregulars, each an island of stars in the vast ocean of space. Their collisions, mergers, and evolutions would shape the universe we see today. But that is a story for another time. The universe, now seeded with the ashes of its first stars, embarked on a new chapter, one of structure and complexity. The primordial gases, enriched with heavy elements, began to coalesce into galaxies, those majestic islands of stars, gas, and dust that dot the cosmic ocean. But galaxies are more than collections of stars. They are dynamic systems shaped by gravity, dark matter, and time. Their births, lives, and deaths are intertwined with the invisible forces that govern the cosmos, and their stories reveal the universe's relentless drive toward order amid chaos. The first galaxies emerged from the darkness like faint sparks. They were small, chaotic, and voracious, feeding on the gas and dark matter that permeated the early universe. These proto-galaxies formed within halos of dark matter, vast, invisible structures that acted as gravitational anchors. Ordinary matter, the hydrogen and helium laced with traces of heavier elements, flowed into these halos, cooling and condensing into stars. The earliest galaxies were likely irregular blobs, lacking the defined spirals or ellipticals we recognize today. Their stars burned hot and fast, their light piercing the thinning cosmic fog. Over time, these fledgling galaxies grew through mergers, cannibalizing smaller neighbors and accumulating gas. Each collision triggered bursts of star formation, lighting up the cosmos with newborn stars. The Milky Way, our galactic home, began its life in this era of turmoil. Born from the mergers of countless smaller galaxies, it grew into a sprawling spiral, its arms winding through space like cosmic whirlpools. At its heart lies Sagittarius A*, a supermassive black hole 4 million times the mass of the Sun. Such black holes are not mere destroyers, they are architects. Their gravitational pull regulates the flow of gas in galaxies, and their immense energy output, jets of particles and radiation, can ignite or quench star formation. The Milky Way's spiral structure, a delicate balance of rotation and gravity, is maintained by the interplay of stars, gas, and dark matter. Its disk, where our solar system resides, is a testament to the stability of such systems, rotating once every 200 million years. Galaxies are not solitary creatures. They exist in clusters, groups, and filaments, bound together by gravity and woven into the cosmic web. The largest structures in the universe, galaxy clusters like the Virgo cluster, contain thousands of galaxies, vast clouds of hot gas, and immense reservoirs of dark matter. These clusters are nodes in the cosmic web, connected by filaments of gas and dark matter that stretch across billions of light years. Within these filaments, galaxies flow like rivers, drawn toward the gravitational pull of the densest regions. The cosmic web is a relic of the early universe's density fluctuations, a frozen echo of the quantum ripples born during inflation. But the evolution of galaxies is not a gentle process. Collisions are common, and when galaxies merge, the results are both destructive and creative. The Milky Way and Andromeda Galaxy, our nearest spiral neighbor, are hurtling toward each other at 110 kilometers per second. In 4.5 billion years, they will collide, a slow-motion dance lasting hundreds of millions of years. Stars, separated by vast distances, will mostly pass unharmed, but clouds of gas will compress, triggering supernovae and birthing new stars. The two supermassive black holes at their cores will spiral toward each other, eventually merging in a burst of gravitational waves. The result will be a giant elliptical galaxy, its stars orbiting in random directions, a chaotic monument to the violence of cosmic union. Yet not all galaxies meet such dramatic ends. Some, like those in the Hubble ultra-deep field, a tiny patch of sky containing thousands of galaxies, fade quietly. As stars age and die, their remnants, white dwarfs, neutron stars, black holes, accumulate. Gas reservoirs deplete, star formation dwindles, and galaxies transition from blue, star-forming spirals to red, quiescent ellipticals. This metamorphosis is driven by both internal and external forces. Supermassive black holes, feeding on infalling gas, can blast energy into their surroundings, heating gas and shutting down star formation. Environmental factors, like the pressure of intracluster gas in galaxy clusters, can strip galaxies of their star-forming material, leaving them barren. Dark matter remains the silent partner in this cosmic drama. Though invisible, it constitutes 85% of the universe's mass. Its gravitational pull shapes galaxies, determines their rotation speeds, and binds clusters together. Without dark matter, galaxies would fly apart. Their stars' orbital velocities defy the predictions of Newtonian gravity based on visible matter alone. This discrepancy, first noted by Vera Rubin in the 1970s, remains one of astronomy's greatest puzzles. Is dark matter a particle waiting to be detected in underground labs? Or does it hint at a modification of gravity itself? The answer eludes us, but its presence is undeniable. Dark energy, a mysterious force driving the universe's accelerated expansion, adds another layer of complexity. Discovered in the late 1990s through observations of distant supernovae, dark energy counteracts gravity on cosmic scales. As the universe expands, galaxies not bound by gravity recede from one another, their light stretched into redder wavelengths. In time, dark energy may tear apart galaxy clusters, then galaxies, and finally atoms, a hypothetical Big Rip. But for now, its influence is subtle, a gentle pressure stretching the fabric of space. The study of galaxies is a window into the universe's past. Light from distant galaxies travels billions of years to reach us, offering snapshots of their youth. The Hubble Space Telescope, peering into the deep field, revealed galaxies as they were just 500 million years after the Big Bang, small, blue, and teeming with star formation. The James Webb Space Telescope, with its infrared vision, pushes this frontier further, capturing galaxies in the era of reionization, their light warped by the expanding universe. These observations reveal a cosmos in flux, galaxies growing and evolving, their histories written in starlight. Yet galaxies are more than scientific curiosities. They are the crucibles of complexity. Within their spiral arms and stellar nurseries, the elements essential for life, carbon, nitrogen, oxygen, are forged and dispersed. Planetary systems coalesce from the debris of dead stars, and on at least one planet, life emerges, evolves, and gazes upward. The Milky Way, a single galaxy among 2 trillion in the observable universe, has given rise to beings capable of contemplating their origins. In this way, galaxies are both the architects and the archives of cosmic history. The story of galaxies is also a story of unanswered questions. How did supermassive black holes grow so quickly in the early universe? What determines a galaxy's shape, spiral, elliptical, or irregular? Why do some galaxies cease forming stars while others thrive? Each mystery invites exploration, from supercomputer simulations of galaxy formation to surveys mapping millions of galaxies. The upcoming Vera C. Rubin Observatory, with its 3.2 gigapixel camera, will scan the sky nightly, tracking the motions of galaxies and probing dark energy's influence. As we unravel these mysteries, we confront the universe's scale. The Milky Way, vast as it is a speck within the Laniakea supercluster, a structure 500 million light-years across containing 100,000 galaxies. Beyond Laniakea lie other superclusters, voids, and filaments, a fractal tapestry stretching to the limits of observation. Yet even this panorama is a snapshot. The universe evolves, its structures growing denser or dissipating, its fate shaped by dark matter and dark energy. Galaxies, then, are more than celestial objects. They are markers of time, their light a bridge between past and present. They remind us that the cosmos is not static but dynamic, a living entity in constant flux. And as we study them, we trace our own lineage, a lineage written in starlight, stretching back to the first flickers of nuclear fusion in the hearts of the earliest stars. Stars are the universe's alchemists. Within their cores, they transmute simplicity into complexity, turning hydrogen into helium, helium into carbon, and carbon into the elements that define planets, oceans, and life. But this alchemy is not gentle. It is born of violence, a cycle of creation and destruction that spans billions of years. From the quiet collapse of a gas cloud to the detonation of a supernova, stars shape the cosmos, seeding it with the ingredients for existence. The birth of a star begins in darkness. A molecular cloud, cold and dense, drifts through the galaxy. These clouds are cosmic nurseries, spanning light years and containing enough gas to form thousands of stars. Within them, turbulence and shock waves, often triggered by nearby supernovae or galactic collisions, create pockets of higher density. Gravity takes hold, pulling gas inward. As the cloud contracts, it fragments into clumps, each destined to become a star. For a star like our Sun, this process takes about 50 million years. The protostar grows hotter and denser until nuclear fusion ignites in its core. Hydrogen nuclei collide and fuse into helium, releasing energy in accordance with Einstein's equation, E equals mc squared. This energy counteracts gravity's crush, establishing equilibrium. The star enters the main sequence, a stable phase where it will spend 90% of its life. But not all stars are so placid. Massive stars, those 8 times heavier than the Sun or more, burn hotter and faster. Their cores reach temperatures exceeding 100 million degrees, enabling the fusion of heavier elements, carbon, neon, oxygen, and eventually silicon. Each fusion stage lasts mere millions of years, a fleeting moment compared to the Sun's 10 billion-year lifespan. These stars are cosmic pressure cookers, layering elements like an onion, hydrogen in the outer shell, helium beneath, then carbon, oxygen, and so on, all the way to an iron core. Iron is a dead end. Unlike lighter elements, fusing iron consumes energy instead of releasing it. When a massive star's core becomes iron, fusion stops. Without outward pressure to balance gravity, the core collapses catastrophically, at nearly a quarter the speed of light, in less than a second. The outer layers, suddenly unsupported, rebound off the collapsing core in a shock wave. The star explodes as a Type II supernova, outshining entire galaxies for weeks. In the heart of this maelstrom, conditions are so extreme that protons and electrons merge, forming neutrons and neutrinos. The core becomes a neutron star, a city-sized object so dense that a sugar cube-sized piece weighs 1 billion tons. Some neutron stars spin rapidly, emitting beams of radiation detectable as pulsars. Others, born with intense magnetic fields, become magnetars, capable of stripping planets of their atmospheres from light years away. But the true marvel of supernovae lies in their debris. The explosion scatters elements forged in the star's core and during the collapse itself. Gold, platinum, uranium, elements heavier than iron, are created in the seconds before the star's death through rapid neutron capture, or the R process. These elements are flung into space, mingling with interstellar gas. Over millions of years, this enriched material becomes part of new stars, planets, and ultimately, life. Not all heavy elements come from supernovae. Neutron-star mergers, collisions of two neutron stars, are cosmic gold mines. In 2017, the LIGO and Virgo gravitational wave detectors observed such a merger. Follow-up telescopes detected a kilonova, a burst of light 1,000 times brighter than a typical nova, rich in heavy elements. The collision produced an estimated 10 Earth masses of gold and platinum, along with radioactive elements like uranium. These events are rare, occurring perhaps once per 100,000 years in a galaxy, but they are critical to the universe's chemical diversity. Smaller stars face quieter fates. A star like the Sun, after exhausting its hydrogen, swells into a red giant. Its outer layers drift away as a planetary nebula, a glowing shell of gas and dust, leaving behind a white dwarf, an Earth-sized ember slowly fading into darkness. But even in death, these stars contribute. The carbon and oxygen in their remnants become part of future molecular clouds. The universe's elemental palette is vast, 94 naturally occurring elements, each with a cosmic origin. Hydrogen and helium were forged in the Big Bang. Elements up to iron were born in stellar cores. Those beyond iron arose in supernovae and neutron star mergers. This hierarchy of creation is etched into the periodic table, a testament to stars' role as elemental architects. Yet the story of stellar alchemy is not just about creation, it is also about distribution. Supernova shockwaves compress nearby gas, triggering new star formation. Stellar winds from massive stars carve bubbles and nebulae, shaping the architecture of galaxies. Even the gentle radiation of low-mass stars influences the chemistry of protoplanetary disks, determining which molecules, water, methane, ammonia, survive to form planets. Our solar system is a product of this cycle. The cloud that birthed the Sun contained debris from multiple supernovae and perhaps a neutron star merger. This diversity is preserved in meteorites, ancient rocks that predate the planets. Carbonaceous chondrites, for example, contain amino acids, the building blocks of proteins, suggesting that life's ingredients are not unique to Earth, but woven into the fabric of the galaxy. Stars also serve as cosmic clocks. By measuring the abundances of radioactive isotopes in meteorites and ancient stars, astronomers can date events in the Milky Way's history. For instance, the ratio of uranium-238 to thorium-232 in old stars reveals that the R process began within the first few hundred million years of the universe, driven by the deaths of the earliest massive stars. But stars are more than element factories. They are beacons, their light encoding secrets of the cosmos. Spectroscopy, splitting starlight into its constituent colors, reveals the fingerprints of elements in a star's atmosphere. Dark lines in the spectrum correspond to absorbed wavelengths, betraying the presence of sodium, calcium, iron, and more. In this way, stars become cosmic Rosetta Stones, their light a language translating the universe's composition. The study of stars also exposes the universe's fragility. A star's lifespan depends on its mass. The smallest red dwarfs, just 8% the Sun's mass, burn dimly for trillions of years. The largest hypergiants, 100 times the Sun's mass, live for less than 1 million years. This disparity underscores a cosmic truth: complexity arises from balance. Too much mass, and stars burn out quickly; too little, and fusion never ignites. Our existence hinges on this equilibrium. Humanity's connection to the stars is literal. The calcium in our bones, the iron in our blood, the oxygen in our lungs, all were forged in stellar cores or supernova explosions. Even the gold in a wedding ring owes its origin to a neutron-star collision that occurred billions of years ago. We are, as Carl Sagan famously said, star stuff contemplating the stars. Yet life's resilience does not guarantee its ubiquity. The universe is 13.8 billion years old, but Earth-like planets may have existed for only the last 8 to 10 billion years. Complex life requires not just the right ingredients but time, time for stars to seed the galaxy with heavy elements, time for planets to cool and stabilize, and time for evolution to explore genetic possibilities. Civilizations, if they exist, may be separated by gulfs of time and space so vast that overlap is improbable. The Fermi paradox looms: if life is common, where are the aliens? Possible answers range from the sobering, advanced civilizations self-destruct, to the speculative, they exist in forms we cannot perceive. Yet the silence may simply reflect the infancy of our search. We have scanned but a fraction of our galaxy, and our tools are still crude. The next decades, with telescopes like the Extremely Large Telescope and the Square Kilometer Array, may bring answers. For now, we inhabit a rare and precious world. Earth's stability is an illusion, a fleeting equilibrium in a cosmos of flux. Plate tectonics recycle carbon, regulating the climate. The moon's gravity stabilizes our orbit. Jupiter shields us from comet impacts. These fortuitous conditions are the culmination of 4.6 billion years of cosmic and planetary evolution. But Earth is not the end of the story. The same processes that shaped our solar system are unfolding around other stars. In the Orion Nebula, the Hubble Space Telescope has captured protoplanetary disks, proplyds, and various stages of planet formation. Some are edge-on, their dark silhouettes rimmed with starlight; others face us, their gaps and spiral arms hinting at nascent planets. Each disk is a laboratory, a testbed for the universal laws of physics and chemistry. The quest to understand planets and life is, ultimately, a quest to understand ourselves. Every exoplanet discovered, every extremophile studied, every molecule synthesized in a lab refines our place in the cosmos. We are not the center of the universe, but we are one of its most intricate expressions, a species born of stardust, shaped by time, and endowed with the curiosity to seek our origins. As we peer into the atmospheres of distant worlds or drill into the ice of Enceladus, we are not merely exploring space. We are tracing the arc of existence, from the singularity to the stars, from the stars to planets, and from planets to life. The journey is far from over. The next chapter lies in the icy plumes of Europa, the methane seas of Titan, and the faint biosignatures flickering in the light of alien suns. Life on Earth has proven to be not just resilient but ingenious, thriving in environments once deemed utterly inhospitable. In the scalding vents of underwater volcanoes, where temperatures exceed 400 degrees Celsius and pressure crushes all but the hardiest organisms, colonies of Thermococcus and Pyrolobus flourish, their existence defying every preconception about the limits of biology. In the bone-dry Atacama Desert, where rain falls once a decade, microbial mats cling to life beneath sun-baked rocks, extracting moisture from the air. High in the stratosphere, bacteria and fungi drift on the edge of space, surviving ultraviolet radiation and freezing temperatures. These extremophiles, life forms that thrive in extremes, are more than biological curiosities. They are proof that life, once begun, is tenacious, adaptive, and capable of exploiting even the harshest niches. And if life can persist in such conditions on Earth, why not elsewhere in the cosmos? The discovery of extremophiles has reshaped our search for life beyond Earth. No longer confined to the notion of habitable zones where liquid water might exist on a planet's surface, scientists now consider a broader spectrum of possibilities. Europa, Jupiter's ice-clad moon, harbors a subsurface ocean twice the volume of Earth's seas, kept liquid by tidal heating as it orbits the gas giant. Hydrothermal vents on its seafloor, much like those on Earth, could provide energy and minerals for microbial communities. Enceladus, a tiny moon of Saturn, sprays plumes of water vapor and organic molecules from fissures in its icy shell, offering a tantalizing glimpse of what might lurk in its hidden ocean. Even Mars, though barren on its surface, may host briny aquifers deep underground, remnants of a wetter past when rivers carved valleys into its rust-colored plains. Then there are the truly alien environments. Titan, Saturn's largest moon, is a world of methane lakes and hydrocarbon dunes, where temperatures hover at -180 degrees Celsius. Here, water is frozen harder than granite, but liquid methane and ethane flow across the surface. Could life exist in such a frigid landscape, using methane as a solvent instead of water? Laboratory experiments suggest that hypothetical cryolife might form cell-like structures from acrylonitrile, a molecule detected in Titan's atmosphere. On Venus, shrouded in clouds of sulfuric acid, aerial microbes could float in temperate layers 50 kilometers above the scorching surface. In 2020, the detection of phosphine, a molecule associated with anaerobic bacteria on Earth, sparked debate about whether Venus clouds might harbor life, though subsequent studies have questioned the finding. These possibilities, however remote, underscore a fundamental truth: life, if it exists beyond Earth, may not conform to our terrestrial biases. The search for extraterrestrial life hinges on identifying biosignatures, chemical or physical traces that indicate biological activity. On Earth, the simultaneous presence of oxygen and methane in the atmosphere is a classic biosignature, as these gases react and neutralize each other unless continuously replenished by life. On distant exoplanets, astronomers hunt for similar imbalances. The James Webb Space Telescope, JWST, with its unparalleled infrared sensitivity, has begun analyzing the atmospheres of worlds like K2-18b, a Hycean planet where temperatures might allow liquid water beneath a hydrogen-rich atmosphere. In 2023, JWST detected traces of dimethyl sulfide, DMS, in its skies, a compound on Earth produced by phytoplankton. While far from conclusive, such discoveries ignite speculation. Yet biosignatures alone are not enough. A planet's context matters. Volcanic activity, geochemical cycles, and stellar radiation can mimic biological processes. To reduce false positives, scientists cross-reference atmospheric data with planetary conditions. Is the world tidally locked, with permanent day and night sides? Does it have a magnetic field to shield its atmosphere from stellar winds? Is there evidence of plate tectonics or water cycling? The TRAPPIST-1 system, with its 7 Earth-sized worlds, offers a testing ground. 3 of these planets orbit within the habitable zone, but their proximity to a volatile red dwarf star, prone to violent flares, raises questions about atmospheric retention. The leap from microbial life to intelligent civilizations is another frontier. On Earth, it took 4 billion years for single-celled organisms to evolve into beings capable of radio telescopes and spaceflight. This trajectory was shaped by countless contingencies: the stability of the climate, the availability of rare metals, even the gravitational influence of the Moon. How universal is this path? The fossil record suggests that complex life arose multiple times. Eyes, wings, and intelligence evolved independently in different lineages, but the emergence of technology is rarer. Dinosaurs dominated Earth for 165 million years without developing agriculture or cities. Intelligence, it seems, is not an evolutionary inevitability but a fragile experiment. This fragility lies at the heart of the Fermi paradox. If the universe is vast and ancient, why have we encountered no evidence of alien civilizations? Proposed solutions range from the sobering to the speculative. The Great Filter theory posits that some stage in the evolution of life, abiogenesis, the transition to multicellularity, or the development of technology, is exceedingly unlikely. If the filter lies ahead of us, it suggests that advanced civilizations inevitably self-destruct. Others argue that spacefaring societies might transcend biological forms, merging with machines or uploading consciousness into digital realms, rendering them invisible to our primitive sensors. Alternatively, we might be alone, a rare fluke in a cosmos indifferent to life. The search for extraterrestrial intelligence, SETI, has scanned the skies for decades, listening for radio signals or laser pulses that betray technological activity. So far, silence prevails. Yet new approaches are emerging. Breakthrough Listen, a decade-long initiative, uses radio telescopes and AI to analyze millions of stars. Optical SETI seeks laser flashes, while others hunt for megastructures like Dyson spheres, hypothetical energy collectors encircling stars. In 2015, the star KIC 846-2852, nicknamed Tabby's star, dimmed erratically, sparking speculation about alien megastructures. Follow-up studies attributed the dimming to dust, but the episode highlights the challenges of distinguishing natural from artificial phenomena. Meanwhile, humanity has begun sending its own signals. The Arecibo message, broadcast in 1974, encoded basic information about Earth's biology and location. The Voyager probes carry golden records with sounds and images of our planet. These efforts, while symbolic, raise ethical questions. Is advertising our presence wise, given the potential risks? Or is curiosity an imperative that transcends caution? The discovery of extraterrestrial life, whether microbial or intelligent, would reshape our understanding of existence. Microbial life would suggest that the universe is teeming with biology, even if intelligence is rare. A signal from an advanced civilization would force us to confront our place in a cosmic community, challenging religions, philosophies, and geopolitical frameworks. Conversely, confirmed solitude would underscore Earth's uniqueness, a fragile oasis of meaning in the void. Yet the cosmos guards its secrets closely. The vastness of space, the limitations of light-speed communication, and the ephemeral nature of civilizations conspire against easy answers. A civilization 1,000 light-years away would receive our radio signals millennia after we sent them, and their reply would take another millennium to reach us. Dialogues would span generations, their relevance fading with time. In the face of such challenges, the search continues, driven by a quintessentially human trait, hope. Hope that we are not alone. Hope that the universe is not just a clockwork void, but a living tapestry. Every extremophile discovered in Earth's depths, every exoplanet analyzed by JWST, every anomalous signal scrutinized by SETI adds a thread to this tapestry. As we peer into the cosmos, we are also peering into our future. The technologies we develop, AI, quantum computing, fusion energy, may one day propel us to the stars. Colonies on Mars, mining outposts in the asteroid belt, and generational ships bound for Alpha Centauri are no longer the stuff of fiction but plausible milestones. Yet these endeavors carry risks. The same ingenuity that might unite us with alien civilizations could also fuel our destruction, a dichotomy as old as fire and the atom bomb. For now, we remain custodians of a pale blue dot, our only home in a universe of wonders. The icy plumes of Enceladus, the methane lakes of Titan, the swirling clouds of Venus, these are not just scientific targets, but symbols of possibility. They remind us that life, in all its forms, is a rebellion against entropy, a defiance of chaos. Whether we find companionship in the cosmos or not, the search itself ennobles us, binding humanity to the stars in a quest as ancient as the first campfire stories and as enduring as the galaxies themselves. The next chapter in this odyssey lies in the uncharted territories of synthetic biology, where scientists engineer organisms to survive on other worlds, and in the icy depths of Europa's ocean, where robotic probes may one day dive. It is a story of robots and humans, of equations and dreams, of silence and signals. The universe, vast and indifferent, waits. The story of cosmic exploration has always been a story of tools. From the first telescopes that revealed Jupiter's moons to the rockets that carried humans to the moon, our understanding of the universe has been shaped by the machines we build. Today, we stand on the brink of a new era, one where our tools are no longer mere extensions of our hands and eyes, but entities with minds of their own. Artificial intelligence and robotics are transforming how we explore space, blurring the line between human and machine, and rewriting the rules of discovery. The Martian wind howls across Jezero Crater, a desolate basin that once held a lake billions of years ago. Here, NASA's Perseverance rover, a six-wheeled robotic geologist, picks its way across the rust-colored terrain. Its mission, to search for signs of ancient microbial life. But Perseverance is not alone. Flying alongside it is Ingenuity, a small helicopter that has become the first aircraft to achieve powered flight on another planet. These machines are more than passive instruments, they are semi-autonomous explorers. Perseverance uses AI to navigate hazardous terrain, choosing its own path around boulders and sand traps. Ingenuity, with its rotor blades spinning furiously in the thin Martian air, relies on algorithms to stabilize itself during flight, adjusting to gusts that could send it spiraling into the dust. Together, they represent a new paradigm in exploration, one where robots act as partners, not just proxies. This shift is born of necessity. The vastness of space, the limitations of light-speed communication, and the harshness of alien environments demand autonomy. A rover on Mars cannot wait 20 minutes for instructions from Earth when it encounters a ravine. A probe diving into the icy plumes of Enceladus must react instantly to unexpected currents. AI enables these machines to think on their own, to learn from their surroundings, and to make decisions in real time. Machine learning algorithms, trained on vast datasets of geological features, allow rovers to identify promising rocks for analysis. Neural networks help spacecraft predict solar storms or navigate through asteroid fields. On the International Space Station, AI-powered systems monitor air quality and radiation levels, alerting astronauts to hazards before they become critical. Yet the role of AI extends far beyond logistics. It is revolutionizing how we process the deluge of data flooding back from space. The Vera C. Rubin Observatory, set to begin operations in Chile, will scan the entire southern sky every 3 nights, generating 20 terabytes of data nightly. No human team could sift through this avalanche of images. Instead, AI algorithms will scour the data for transient phenomena, supernovae, asteroid movements, gravitational lensing events, flagging the most intriguing for human review. Similarly, the James Webb Space Telescope employs machine learning to calibrate its instruments and optimize its observations, ensuring that every precious minute of observing time is used wisely. The marriage of AI and robotics is also opening frontiers once deemed unreachable. Consider the Moon. By the 2030s, NASA's Artemis program aims to establish a sustainable human presence there. But before astronauts arrive, robots will lay the groundwork. Autonomous bulldozers will level landing pads, while 3D printers, guided by AI, will construct habitats using lunar regolith. These robots will operate in packs, communicating via a localized internet and sharing tasks. A rover might scout a site, map it in 3D, and relay the data to a printer, which then builds a radiation-shielded dome without human intervention. Meanwhile, in the permanently shadowed craters of the lunar South Pole, robotic prospectors will hunt for water ice, a resource critical for life support and rocket fuel. The outer solar system, too, is becoming a playground for autonomous machines. Europa Clipper, NASA's upcoming mission to Jupiter's icy moon, will carry AI-driven instruments to analyze plumes erupting from the subsurface ocean. If it detects organic molecules or thermal signatures suggestive of hydrothermal vents, the probe could adjust its orbit in real time to investigate further. Farther out, on Titan, a proposed drone named Dragonfly will use AI to navigate the moon's thick atmosphere, avoiding methane storms as it hops between sites of interest. But the true test of machine autonomy lies in interstellar exploration. Breakthrough Starshot, a visionary project to send gram-scale probes to Alpha Centauri, hinges on AI. These nanocraft, propelled by laser sails, would travel at 20% the speed of light, reaching the nearest star system in 20 years. During their flyby, they would have mere hours to photograph planets, analyze atmospheres, and transmit data back to Earth. With no chance for human intervention, the probe's AI must decide what to observe, how to prioritize data, and when to maneuver, all while hurtling through an alien star system at relativistic speeds. As machines grow more capable, they raise profound questions about the future of human spaceflight. Will astronauts become obsolete, replaced by swarms of robots that build, explore, and even think for themselves? Or will humans and machines forge a symbiotic relationship, each compensating for the other's weaknesses? The answer lies in the challenges ahead. On Mars, where radiation and isolation threaten human health, robots could prepare habitats, grow food, and maintain equipment ahead of crewed missions. In the asteroid belt, autonomous mining drones could extract water and metals, fueling humanity's expansion into the solar system. And in the search for extraterrestrial intelligence, AI could decode signals too subtle or complex for human analysts to recognize. Yet for all their prowess, machines lack the why of exploration. They do not marvel at Saturn's rings or ache to walk on distant worlds. This is humanity's role, to dream, to dare, and to imbue the cosmos with meaning. The best explorations will blend human intuition with machine efficiency. Picture a future Mars base, where astronauts direct a fleet of AI rovers from a habitat dome. The humans decide where to explore, a curious rock formation, a dry river delta, while the robots determine how, calculating the safest path or the optimal drilling angle. Or imagine a deep space mission to a rogue planet, where a human crew in suspended animation is tended by an AI that monitors their vitals, repairs the ship, and wakes them only when something demands their judgment. In the beginning, there was nothing. No stars, no galaxies, no light. Not even emptiness, for emptiness implies space, and space did not yet exist. There was only a singularity, a point of infinite density and temperature, compressed into a realm smaller than the nucleus of an atom. Time, as we understand it, had no meaning here. The concepts of before and after dissolved into a state beyond human comprehension. This singularity was the entirety of the universe, a dimensionless spark containing all the energy, matter, and potential that would one day become galaxies, planets, and life. Then, in a cataclysm that defies analogy, the singularity erupted. This was not an explosion in space, but the explosive birth of space itself. The Big Bang marked the beginning of time, space, and the fundamental forces that govern reality. In the first fractions of a second, the universe underwent a phase of exponential expansion known as cosmic inflation. Space stretched faster than the speed of light, growing from smaller than a proton to the size of a grapefruit in less than a trillionth of a second. This rapid stretching smoothed the universe into a nearly uniform expanse, but left behind faint imprints, quantum fluctuations. These microscopic ripples, born from the chaotic froth of the early universe, were stretched into cosmic proportions, becoming the seeds of all future structure, galaxies, stars, and planets. As the universe expanded, it cooled. Energy transformed into matter, guided by the nascent laws of physics. Quarks and gluons, the building blocks of protons and neutrons, condensed out of the searing plasma. For the first 3 minutes, the universe was a nuclear furnace. Protons and neutrons collided, forming the nuclei of light elements, hydrogen, helium, and traces of lithium. Yet the universe remained a scorching, opaque fog. Free electrons, charged and restless, scattered photons relentlessly, trapping light in a chaotic dance. This epoch lasted 380,000 years. Then, as temperatures dropped to a few thousand degrees, electrons slowed enough to be captured by atomic nuclei. Neutral atoms formed, and the universe became transparent. Light, finally free to travel, streamed outward in all directions. This primordial glow, now cooled to microwave wavelengths, permeates the cosmos as the cosmic microwave background, CMB. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB is the oldest light in the universe, a snapshot of its infancy. Its subtle temperature variations, tiny fluctuations of 1 part in 100,000, mirror the density variations imprinted during inflation. These fluctuations would become the scaffolding for the cosmic web, the vast network of galaxies and dark matter that defines the large-scale structure of the universe. Gravity, the weakest of the fundamental forces but relentless in its pull, began sculpting the cosmos. Regions slightly denser than their surroundings exerted a stronger gravitational tug, drawing in gas and dark matter. Over millions of years, these overdense regions collapsed into halos of dark matter, within which the first stars ignited. These stars, known as population 3 stars, were unlike any that exist today. They were behemoths, hundreds of times the mass of the Sun, composed almost entirely of hydrogen and helium. Their lives were brief and violent. Burning through their nuclear fuel in mere millions of years, they died in spectacular supernovae, seeding the cosmos with heavier elements. Carbon, oxygen, silicon, and iron, the building blocks of planets and life, were forged in their cores and blasted into space. The death of these first stars marked the end of the universe's dark ages. Light from their explosions ionized the surrounding gas, creating bubbles of transparency in the cosmic fog. Over time, these bubbles merged, and the universe became fully reionized, a process that took hundreds of millions of years. This era, known as the Cosmic Dawn, set the stage for the formation of the first galaxies. Galaxies began as tiny knots of gas and dark matter, merging and growing through collisions. The Milky Way, our galactic home, started forming roughly 13.6 billion years ago. Its spiral arms, brimming with stars and nebulae, are the product of countless mergers with smaller galaxies. At its heart lies Sagittarius A*, a supermassive black hole with a mass 4 million times that of the Sun. Such black holes are not cosmic anomalies, they reside at the centers of most galaxies, their growth intertwined with the evolution of their hosts. Yet much of the universe's mass remains unseen. Dark matter, an invisible substance that does not interact with light, outweighs ordinary matter by a factor of 5. Its gravitational pull binds galaxies and galaxy clusters, preventing them from flying apart. Despite decades of searching, its nature remains elusive. Is it a particle? A remnant of higher dimensional physics? The answer lies beyond our current understanding. The story of the universe is one of transformation, from a featureless singularity to a cosmos teeming with structure. It is a tale written in the language of physics, etched into the fabric of space-time. And it is far from over. Billions of years from now, the Milky Way will collide with the Andromeda Galaxy, stars will fade as fuel runs out, and the universe will continue expanding, perhaps forever. But for now, we are here, alive in a fleeting moment of cosmic history, striving to unravel the mysteries of our origins. The universe, now transparent and cooling, entered an era of darkness, a darkness not of emptiness, but of potential. The cosmic microwave background glow had faded into the infrared, and the primordial gases of hydrogen and helium settled into vast, silent clouds. These clouds, drifting through the expanding cosmos, were the cradles of the first stars. But these stars would not resemble the ones we see today. They were cosmic pioneers, born in a universe devoid of the elements that now define planets, oceans, and life. The birth of the first stars began with gravity's patient pull. Tiny density fluctuations in the primordial gas, imprinted during inflation, slowly amplified. Dark matter, invisible and mysterious, played a critical role. Its gravitational influence created halos, invisible scaffolds that drew hydrogen and helium into dense clumps. Within these halos, gas accumulated, growing hotter and denser until nuclear fusion ignited. These first stars, known as population 3 stars, were unlike anything that exists in the modern universe. They were colossal, often hundreds of times more massive than the Sun, and composed solely of hydrogen and helium. Without heavier elements to aid in cooling, their formation was a violent, inefficient process. Turbulent gas collapsed directly into monstrous stellar embryos, their cores reaching temperatures of over 100 million degrees. The lives of these stars were brilliant and brief. Burning hydrogen at a ferocious rate, they lived for only a few million years, a cosmic blink. Their sheer mass doomed them. The intense radiation pressure in their cores could not counteract the crushing weight of their outer layers. When they exhausted their hydrogen fuel, they collapsed and rebounded in cataclysmic explosions known as pair-instability supernovae. These explosions were unlike any seen today. The entire star was obliterated, leaving no remnant, no black hole, no neutron star. Instead, they ejected their entire mass into space, scattering the first heavy elements into the cosmos. Carbon, oxygen, nitrogen, and traces of iron were forged in their cores and expelled in these explosions, seeding the universe with the raw materials for future stars, planets, and life. But not all population 3 stars died so completely. Smaller ones, if small can describe stars dozens of times the sun's mass, collapsed into black holes. These black holes, primordial and ravenous, began accreting gas and merging with one another. Over time, they grew into the supermassive black holes that now anchor galaxies. Their growth released torrents of radiation, carving bubbles of ionized gas in the surrounding hydrogen. This marked the beginning of the epoch of reionization, a transformative era when ultraviolet light from the first stars and black holes stripped electrons from atoms, rendering the universe transparent once more. The death of the first stars reshaped the cosmos. Their explosions lit up the darkness, and their ashes enriched the interstellar medium. This enrichment was pivotal. Heavier elements, referred to as metals in astronomy, acted as catalysts for future star formation. They allowed gas clouds to cool more efficiently, fragmenting into smaller, more stable clumps. The second generation of stars, population 2, formed from this slightly metal-enriched gas. These stars were smaller, longer-lived, and more efficient. Some still burn today in the oldest globular clusters of the Milky Way, their atmospheres bearing the faint chemical signatures of their massive progenitors. As generations of stars lived and died, the universe grew more complex. Supernovae, neutron star mergers, and stellar winds continued to pollute the interstellar medium with heavier elements. By the time the Sun formed 4.6 billion years ago, the gas cloud that birthed it contained traces of every naturally occurring element: carbon for organic molecules, oxygen for water, iron for planetary cores, and gold for jewelry. This alchemy, the transformation of simple elements into complex ones, is the legacy of stars. Every atom in our bodies, save the primordial hydrogen, was forged in the heart of a star or the chaos of its death. Yet the stellar life cycle is not infinite. As the universe ages, star formation slows. Gas clouds are depleted, and galaxies grow dimmer. The Milky Way star formation rate peaked 10 billion years ago and has since declined. In 100 trillion years, the last stars will fade, leaving the universe dark and cold. But for now, the stellar forge burns bright, its flames kindling the potential for life. The next chapter in this saga is the formation of planets, the transition from elemental abundance to habitable worlds. From the dusty disks around young stars to the delicate balance of atmospheres, planets are the crucibles where chemistry becomes biology. But that is a story of delicate balances, cosmic accidents, and the resilience of life. In the aftermath of stellar explosions, amid the swirling debris of supernovae and neutron star mergers, the universe began crafting its most delicate masterpieces, planets. These worlds, rocky spheres, gas giants, icy moons, are the products of chaos and precision, born from the interplay of gravity, chemistry, and chance. Their formation marks the transition from elemental abundance to environments where atoms assemble into molecules, molecules into minerals, and minerals into landscapes. And on at least one world, this alchemy crossed a threshold, transforming inert matter into living, breathing complexity. The story of planets begins in the circumstellar disks that encircle young stars. These disks, remnants of the same molecular clouds that birthed their parent stars, are cradles of creation. Composed of gas, dust, and ice, they span hundreds of astronomical units, their particles colliding, sticking, and growing in the gentle glow of stellar infancy. The process is incremental, almost imperceptible. Micron-sized dust grains, rich in silicates and carbon compounds, cling together through electrostatic forces, forming fractal-like aggregates. These clumps grow to pebbles, then boulders, and eventually kilometer-sized planetesimals, the building blocks of planets. In our solar system, this process unfolded 4.6 billion years ago. The Sun, newly ignited, bathed its protoplanetary disk in heat and light. Close to the star, temperatures were too high for volatile compounds like water and methane to condense. Here, only metals and silicates could solidify, forming the rocky seeds of terrestrial planets, Mercury, Venus, Earth, and Mars. Farther out, beyond the frost line, a boundary where sunlight's warmth fades, ices of water, ammonia, and methane froze into solid particles. These ices, abundant and sticky, accelerated the growth of planetesimals, allowing them to amass gargantuan atmospheres of hydrogen and helium. This is how the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune, came to dominate the outer solar system. But planet formation is not a serene progression. It is a violent ballet of collisions and near catastrophes. Planetesimals jostle for dominance, their orbits destabilized by gravitational interactions. Some merge, their impacts releasing enough heat to melt rock and metal, creating molten globules that differentiate into cores and mantles. Others shatter, scattering debris that will later form moons or rings. In the early solar system, Earth was struck by a Mars-sized protoplanet named Theia. The collision vaporized both bodies, ejecting a cloud of molten debris that coalesced into the Moon. This violent birth stabilized Earth's axial tilt, granting it stable seasons, a critical factor for the evolution of life. Jupiter, the solar system's behemoth, played a dual role as both protector and disruptor. Its immense gravity shepherded asteroids into the belt between Mars and Jupiter, preventing them from bombarding the inner planets. Yet during its migration inward and then outward, a dance known as the Grand Tack hypothesis, it likely scattered icy bodies into the inner solar system, delivering water to Earth. Comets, those icy remnants of the outer disk, became cosmic couriers, ferrying water and organic molecules to the young planet. Water, the elixir of life, is a paradox. Though abundant in the universe as ice, its presence in liquid form requires a delicate balance. A planet must orbit within its star's habitable zone, where temperatures allow water to persist as a liquid. Too close, and water evaporates; too far, and it freezes. Earth's position in this Goldilocks zone is fortuitous, but not unique. The Milky Way harbors billions of stars with habitable zones, and recent discoveries suggest that rocky planets in these regions are common. The ingredients for life, however, extend beyond water. Complex organic molecules, amino acids, sugars, nucleobases, are ubiquitous in space. They've been found in meteorites, comets, and the interstellar medium. The Murchison meteorite, which fell in Australia in 1969, contained over 90 amino acids, many unrelated to terrestrial life. These molecules likely formed in the protoplanetary disk, catalyzed by ultraviolet light and cosmic rays. When they rained down on early Earth, they found a world primed for experimentation: volcanic landmasses, tidal pools, and hydrothermal vents. Hydrothermal vents, both on land and beneath the ocean, are crucibles of prebiotic chemistry. In their mineral-rich waters, heated by geothermal energy, simple molecules assemble into more complex structures. Lipids form membranes, RNA molecules self-replicate, and metabolic pathways emerge. The transition from chemistry to biology is not a single event, but a continuum, a series of steps as atoms and molecules explore the possibilities of structure and function. Yet Earth is not the only world where these ingredients converge. Mars, once a warmer, wetter planet, bears evidence of ancient rivers and lakes. Its soil contains organic molecules, and its subsurface may harbor liquid water. Europa, a moon of Jupiter, hides a global ocean beneath its icy crust, warmed by tidal flexing. Enceladus, a moon of Saturn, spews water vapor and organic compounds from geysers at its south pole. Even Venus, a hellish world with surface temperatures hot enough to melt lead, may have had temperate oceans billions of years ago. The discovery of exoplanets, planets orbiting other stars, has expanded our understanding of planetary diversity. The Kepler Space Telescope revealed worlds unlike anything in our solar system, hot Jupiter's gas giants orbiting closer to their stars than Mercury does to the Sun, super-Earths, rocky planets up to 10 times Earth's mass, and mini-Neptunes, gaseous worlds smaller than Neptune but larger than Earth. The TRAPPIST-1 system, 40 light-years away, contains 7 Earth-sized planets, 3 of which orbit within the habitable zone. Their compact arrangement, all 7 could fit within Mercury's orbit, hints at the variety of planetary architectures. Characterizing these distant worlds is a feat of ingenuity. Astronomers use the transit method, detecting dips in starlight as planets pass in front of their stars, and the radial velocity method, measuring the star's wobble caused by planetary gravity. New technologies, like the James Webb Space Telescope, analyze starlight filtered through exoplanet atmospheres, identifying molecules like water vapor, methane, and carbon dioxide. In 2023, JWST detected dimethyl sulfide in the atmosphere of K2-18b, a Hycean world, a possible biosignature, though not yet confirmed. The search for life beyond Earth hinges on these biosignatures, chemical or physical markers that suggest biological activity. On Earth, the coexistence of oxygen and methane in the atmosphere is a telltale sign of life, as these gases react and would neutralize each other without constant replenishment. Other potential biosignatures include the red edge of vegetation, a reflectance signature of photosynthesis, or artificial pollutants in an atmosphere. But life, as we know it, is tenacious. On Earth, extremophiles thrive in environments once deemed inhospitable, boiling hydrothermal vents, acidic hot springs, the frozen deserts of Antarctica. If life exists elsewhere, it may have adapted to conditions we can scarcely imagine, subsurface oceans on icy moons, methane lakes on Titan, or the airborne droplets of Venus clouds. Venus, long dismissed as a lifeless inferno, has recently sparked intrigue. In 2020, scientists detected phosphine in its atmosphere, a molecule typically produced by microbes or industrial processes. While the discovery remains controversial, it underscores the unpredictability of astrobiology. Life, if it exists there, would defy all Earth-based paradigms, persisting in clouds of sulfuric acid at altitudes where temperatures and pressures are eerily Earth-like. The emergence of life on Earth, roughly 3.7 billion years ago, coincided with the end of the late heavy bombardment, a period when the inner solar system was pummeled by asteroids and comets. This timing suggests that life arose swiftly once conditions stabilized. The oldest fossils, stromatolites found in Western Australia, date to 3.5 billion years ago, their layered structures built by microbial mats. These early organisms were prokaryotes, simple, single-celled life without nuclei. For over 2 billion years, they were the sole inhabitants of Earth, their metabolism slowly transforming the planet. Cyanobacteria, harnessing sunlight through photosynthesis, began pumping oxygen into the atmosphere 2.4 billion years ago. This great oxidation event was a catastrophe for anaerobic life, but a boon for complex organisms. Oxygen's high energy potential enabled the evolution of eukaryotes, cells with nuclei and organelles, and, eventually, multicellular life. The rest is evolutionary history: the Cambrian explosion, the age of dinosaurs, the rise of mammals, and the ascent of a species capable of reflecting on its origins.
Thank you for trusting Sleep Scholars with your quiet moments. To our writers, your words are the heartbeat of this channel. To James, your voice turns science into solace. And to you, if you'd like to make this a ritual, hit subscribe. We'll be here, always ready to help you unwind. Sleep well, and we'll see you soon.